Hello, my name is Daniel Pyrek, and I will be giving a talk about aquaculture for the 60/20 seminar. It will be about the CUSD, or Cornell University Sustainable Project Team, Fish and Artificial Intelligence Monitoring Team, which I am currently co-leading. Alright, so first I'll be going over a general background of aquaculture, and then I'll talk about my stakeholders and advisor, then the objectives of the project, which encompasses which different recirculating aquaculture parameters we are going to be monitoring, and then the data pipeline that will feed into our machine learning system. Begin with a background on aquaculture. So there is a 40 million metric ton increase in seafood demand expected by the end of the decade, and this is largely due to an increasing world population, as well as an increase in protein demand. So aquaculture has risen to the challenge, and it is essentially the harvesting of animal and plants in different types of water environments. On the right you can see a graph that shows the relative production of aquaculture to wild capture. You can see that wild capture has leveled off, and we've essentially entered a steady state, whereas aquaculture continues to produce with increasing demand. This aquaculture increase has provided year-round jobs and is helping rebuild protected species and habitats, and also supports an increasing protein demand. Globally, aquaculture currently accounts for 50% of all seafood production for human consumption. However, this percentage is expected to continue to grow. So what is a recirculating aquaculture system, or RAS? Well, let's begin with common aquaculture methods. The first one is the pond culture, which utilizes either man-made or natural ponds to grow and house fish and plants. The second one is a cage culture, which uses mesh enclosures to either grow fish in salt or freshwater. Raceway cultures utilize a channel which can continuously flow water through the tanks to flush out any kind of waste. And recirculating aquaculture systems, as seen in these two pictures, use the same water source, run them through the tanks, and then purify it so that it can continuously recirculate through all the systems. Aquaculture does face certain challenges. The first one is that industrial feed constitutes of upwards of 60% of aquaculture production costs. Oftentimes, feed is the most prohibitive challenge to the growth of the industry. Second problem is that uneaten feed can clog filters and dirty the water. Uneaten feed and fish waste often create ammonia, which is actually harmful to the fish. A third problem is that less quantified problems such as disease, stress, and mechanical failure can lead to unexpected large fish losses. A fourth problem can be relatively high energy usage. I'll quickly go over the project objectives. The first one is to identify cues in video, audio, and water parameter data that correlate to fish feeding status and health. So we have to figure out what things about the fish make them seem hungry, sick, or unhealthy. The second one is to design and build a module that can automatically collect this data and then store it into the cloud for us to use. The third one is to use the sensory data to train a machine learning model that can actually decide when the fish are in these different states. We've made pretty significant headway onto these 3 bullet points, and the next 3 are ones that we hope to continue in the future. The fourth one is to develop an interface to provide real-time data from individual fish tanks to operators. This way an operator can quickly tell when a tank has an issue. The fifth one is to use the algorithm that we developed and real-time data to control robotic feeders based on hunger cues to feed the fish automatically. The sixth one is to compare the growth performance of fish fed by our system compared to ones that are traditionally used now, and see which one is better and if we've improved. The team consists of faculty from the College of Agricultural and Life Sciences, Dr. Eugene Wan in Animal Science, Dr. Michael Timmons from Biological and Environmental Engineering at CALS, and from the College of Engineering, Dr. David Schneider in Systems Engineering, who's currently the head advisor to CUSD, and of course all the students within the CUSD team. I would like to give you a little context to what a feeding event in one of these tanks looks like. So here's a video from a aquaculture facility on campus, and you can see that whenever the operator throws in the feed, that all the fish come up and they're very aggressively fight one another for it. And this is very normal behavior for these large fish. And you can see how loud and how much movement there is. And this is something that Professor Michael Timmons often calls the splash factor, and that's something that we hope to track, because this means that the fish are definitely healthy and more hungry, whereas maybe less healthy fish would be less aggressive while they feed. So based on the video you just saw, we kind of looked at the different parameters that we could collect and what we were interested in. So oftentimes most of these facilities already collect data on the water level, aeration such as dissolved oxygen, temperature, and pH, just to make sure that the fish are getting their basic essentials. However, these new parameters that we could collect are things like sound, video, maybe different kind of water movement speeds and things as the fish swim in circles, and these are all things that are collected by our module and then are analyzed and then brought over to the operator. So what is machine learning? Well, it provides systems the ability to automatically learn and improve from experience without explicitly being programmed. Essentially, we will be using supervised training, which requires a team to take a bunch of data that we collect and then manually categorize it into different bins for the algorithm to practice with. And then once the program has continued to practice, it will be successful enough to take data it's never seen before and then categorize it on its own. And this whole process takes a lot of data. So this begs the question of how are we as a team going to categorize this data to teach our program to identify problems? Well, the first one we want to start with is feeding and not feeding events. We want the computer to be able to identify, oh, I am looking at the fish feeding, and that's a good simple starting goal. From there, we want to have the computer identify infrequent feeding events versus frequent feeding events. And then eventually, if we can find a way to do this in the lab, is healthy versus unhealthy fish in general. And by feeding in large collections of data within these different categories, we can get the computer to be able to identify an unknown image or data from these categories and learn on its own, even if it's never seen that frame or that data before. So this is an interesting benefit because there are a large amount of different fish that are farmed at these systems. In order to collect the data for carp, tilapia, salmon, and different conditions, different looking tanks, it'd be very difficult. But if we feed in a lot of data into these categories, we can get the computer to learn on its own what these look like in general and be able to make those decisions for itself without explicitly ever telling it what a carp or a salmon look like. We actually gathered some data from these aquaculture tanks, and this is just a little snip of it, but as you can see, there are kind of fluctuations that happen naturally throughout the day. For instance, the water temperature and the pH change, and it's pretty interesting because sometimes dissolved oxygen can dip due to feeding events. So while they're metabolizing all that food and aggressively swimming around, they actually will use more dissolved oxygen in the tank. So that's something that is already being monitored in these tanks that we might be able to utilize to try to track their feeding events and their satiation. The next parameter that we think would be interesting to collect data in is audio. So on the left you can see kind of a histogram throughout a feeding event, and you can see the mean is roughly around 57, 54, and these are in decibel ratings. And so it'd be interesting to compare different feeding events and see kind of what is the mean or median of decibel ratings of these different feeding events, and therefore you can maybe draw some conclusions that these are less or more aggressive. So if you feed your fish too frequently, maybe the sound decreases during that feeding event, and that means that maybe they're less hungry, so they splash less aggressively. Whereas maybe if you're feeding them too infrequently, where you should be feeding them more so that you're getting them to grow as quickly as possible, you'll hear these louder decibel readings, which will indicate that they're more hungry. On the right, you can see actually the decibel reading before feeding event, and around in the middle of that graph, you can see that it jumps up from around 50 decibels on average to about 60 during that feeding event, and slowly starts to decrease back to the 50. So these kind of clues might indicate if they're healthy or not, and then we can adjust accordingly as the program learns to what is the optimal feeding schedule, and maybe find some inconsistencies that might indicate that the fish are unhealthy. The next novel parameter that the team is investigating is video. Video is taken of the fish tanks, parsed into frames, and then categorized where it's fed into the machine learning algorithm. The computer will then learn what videos that it's fed into it fall into which categories. And this is an interesting benefit because with our own eyes, we might not be able to differentiate a healthy versus unhealthy case. However, if we categorize these images and videos and feed them in, the computer might pick up on some nuanced changes in the tanks that could actually help it differentiate between those two cases. This is being run in TensorFlow, and we've actually been able to feed in some frames and videos and get the computer to identify, oh, this is a feeding event and this is not a feeding event. And we're hoping to continue to refine it so that, and with more categories, so it can pick on some things that a human operator might never be able to see. Another parameter the team is tracking is water's movement. So we set up an experiment where we put a buoy with a dot in a bucket and splashed at different levels of strength, and then tracked with a computer program the movement of that dot on the buoy. And you can see here in this video the team member is splashing, and then kind of you can see that the buoy is moving, but it's tethered to the bottom of the bucket. On the right, you can see a graph, and it shows that there was actually a pretty significant increase in the amplitude of the buoy moving side to side in the x direction as the strength of the splashing increased. So that's another thing that we might pursue. So now that I've gone over all these different parameters that we can track, how does this really help the operator? Well, the computer program will take all of this different data that we've collected and then create kind of these different cases where it can identify if fish are healthy, unhealthy, etc. in those bins I talked about. And it can sometimes find those very subtle changes between the different parameters that a human operator might not be able to see. So we're actually going to be partnering with Cargill and the dashboard that they've created to actually allow the operator to very easily see the different parameters and levels within each tank, and then have our program notify the operator if something is wrong in each individual tank, so the operator can go and check. Because right now the standard is oftentimes someone will just walk from tank to tank and just kind of eyeball it and see if they can spot any kind of problems, and that is not a very efficient way for the industry to continue. Thank you so much for listening. This was a little odd because it's my first recorded lecture, so it's kind of strange talking to myself. But yeah, I appreciate your time, and if you have any questions, please just write them down below in the discussion. Thank you so much.